So in this lecture, I will continue to discuss the central limit theorem. So the theorem we proved in the previous lecture, I will repeat it here. You take a sequence xj of independent random variables, and I will take it now in the general sense. So actually, I'll consider an array. And now J, it's running from 1 up to Kn. And Kn, it's a sequence which increases to plus infinity. I will assume that the expectation of these random variables x and j, it's equal to 0, and that the sum of their second moment, it's equal to 1. So the expectation of x and j square, it's equal to 1, and this for all n larger than 1. So remember, here we have an array. At level 1, we have x11 up to x1k1, and at level n, we have xn1 up to xnkn, and the assumption of independence is saying that for each n, these a finite number of random variables are independent. So this is the first assumption. And then we proved that the Linbec condition, which can be written in this context as follows. So I'm taking the sum from 1 up to kn of the integral over x larger than epsilon of x squared d mu and j. So mu and j, it's the distribution measure associated to the random variable x and j. I'm summing that over j, and I'm saying that for all epsilon positive, this sum converges to 0. So what we proved is that under these conditions, then the sum of x and j from 1 up to kn, converge to a Gaussian random variable with mean 0 and variance 1. So this sequence converges in distribution to a random variable which has mean 0 and variance equal to 1. So this is what we proved, and we also proved that this Lindbergh condition, so this is called, remember, the Lindbergh condition, also shows that if you take the sum from 1 up to kn of the probability that x and j larger than epsilon, that this converges to 0 for all epsilon converging, for all epsilon positive. And this convergence is as n tends to infinity. So we proved in the last lecture these two consequences of the Lindbergh condition. So now we will soon start to investigate the convergence of this type of sequence. So we would like to find conditions which ensure that such a sequence, and here the assumptions I'm having in mind are that these random variables are independent, so that in the sense that for each n, the random variables x and j from 1 to kn are independent, where kn is a sequence which converges to infinity. These sequences, they have mean 0. Let's say that their variance are equal to 1. And I want, under these conditions, find conditions which ensure that this sum converge in distribution to some random variable. Of course, if I want this sum to converge, I need that these random variables to be small. If one of them, say, does not depend on n, or it keeps, as n goes to infinity, remains large, well, this convergence might fail because, well, this random variable will have a weight in the limiting behavior of this sum. So in some sense, we want first to impose that each of these variables is negligible. So, and there are many ways in which we can write down such a condition. So we could, for instance, the first condition which comes to mind is that, well, maybe we want to ask that for any fixed j, x n j, it's small. It's small in which sense? Say in probability. So that could be a condition imposing, say, that for all epsilon and for all fixed j, this limit is equal to 0. Of course, this is not a sufficiently strong condition because we would like all such variables to be small, and this condition does not guarantee that xn, kn is small since j is kept fixed. So this is not a good condition. We have to introduce a condition in which all j's are involved. So we can replace this condition by a stronger condition which says that the limit in n of the maximum of j's of this probability converge to 0. So here we are guaranteeing that all these variables are small in probability sense. So that we will impose that for all epsilon positive, then we have that condition. And well, this condition, we can of course impose stronger condition as this one. This one is clearly stronger than that one, but this one is strong enough. So what we would like to investigate in this next lecture is the following problem. Assume that you have a sequence x and j, or a sequence of sequences, which means that an array of random variables in this sense, that for each row we have a fixed number of random variable, and this number it's increasing to plus infinity. And on each row, these random variables are independent. Assume that have mean 0, you fix the total variance of these random variables to be 1, say, and you'd like to investigate the convergence of the sum in distribution as n goes to infinity. So in this sense, so let me add this assumption to these three assumptions we had in the previous theorem. So I'm adding to these conditions the condition that the limit as n goes to infinity of the maximum from j from 1 up to n of the probability that x n j is larger than epsilon, and requiring that for all epsilon this is equal to 0. So we have seen that the Lindbergh condition implies this condition, which is stronger than that condition. So in particular, Lindbergh condition implies that condition. And Lindbergh condition implies also the convergence to the Gaussian random variable. So today, what I will prove is that under this condition, so I'm assuming that condition, we have that if this sum converge to the Gaussian, then the Lindbergh condition holds. So this is a converse to the previous theorem. So in the previous theorem, we are showing that Lindbergh condition implies this condition on the negligibility of the random variables x and j and the convergence in distribution. Now, today, we will prove that if we have this condition and the sum converge to a Gaussian 0, 1 random variable, then the Lindbergh condition is in force. And But I want you to read this theorem as follows. Well, assume that we have these 4 conditions. Then Linbec condition, it's necessary and sufficient for the convergence to a Gaussian random variable. So we have here, in this problem, we have a necessary and sufficient condition to ensure convergence to a Gaussian random variable. And then you can ask, well, maybe I want now to take another type of sequence, x and j, which still satisfy this uniform negligibility condition, but which does not satisfy the Lindbergh condition, and see, well, what are the possible limits of this sequence, and are there necessary and sufficient conditions which ensure that this sequence converge to a certain law. So today I will prove the converse of Lindbergh theorem, and then I'll start to address in the next lecture this problem, first by trying to characterize what are the possible limits of such sequences, and then try to find sufficient conditions which ensure the convergence of this sum to to a law, to some distribution in the limit. So this is the plan. So the theorem I want to prove today, this is the main theorem, reads as follows. Well, I called N this assumption, G this assumption. So we have these 3 assumptions which I'm always assuming. And what I want to prove is that if I have condition N and condition G, N for negligibility and G for Gaussian limit, then the Lindbergh condition holds. So this is the main theorem today, which gives you a converse of the theorem I proved in the previous lecture. Now, before I prove this theorem, I want to have a closer look at this condition. So I want to prove the following lemma, is that condition N holds if and only if I consider the characteristic function phi n j of the random variable x and j, I take its difference to 1. I know that at 0 this is 1. This is telling me that these random variables are small, so I expect f and j to be close to 1. If I take the maximum over j, and I take a supremum over t less than t, then this converges to 0 as n goes to infinity. So I want to prove that this condition is equivalent to this condition, which can be written in terms of the characteristic function. And I'm sorry, because the proofs and the arguments will be very close to the proofs and arguments of the previous lecture, but I want to make it this statement very clear, because it's very important to understand that this central limit theorem, this result which has been proved in the last lecture, it's actually part of a larger picture in which you want to investigate how this behaves asymptotically. So I will erase everything. I'll prove this first lemma, and then I will come back to prove the main theorem of this lecture. So this is the lemma I want to prove, that for these 2 conditions are equivalent. First one is that for every epsilon, these maximum converge to 0. I didn't write it. And the second one is that for all t, these supremum converge to 0. So let's first prove one of the directions. Let's assume that this maximum is converging to 0, and let's start to estimate it phi n g t minus 1. So this, by definition of the characteristic function, can be written as the exponential I tx d mu n j x minus 1, but I can insert the minus 1 inside the itx and to write it in this way. Now, at this point, I want to divide this expression this integral in two pieces. I will fix an epsilon positive and consider the piece in which x is bounded by epsilon, and then a second piece in which x is larger than epsilon. And once I divided the integral in two pieces, I can pass the absolute value inside. Now, for this first integral, I'll just use the inequality that exponential I z minus 1, that this is bounded by a constant c0 times the absolute value of 0, and this holds for all z in C, complex number z. And while for this second piece, I'll just use that this expression is bounded by 2. So once I do that, what I have, it's here z, it's tx. So what I appear, it's a constant z times t times x. T, it's, let's say, bounded by capital T. So this is bounded by capital T. The integral for x less or equal than epsilon, x d mu and j. So this is the first piece. And for the second piece, I just have times plus 2 times the measure of this set. But the measure of this set, it's the probability that the random variable x and j, it's larger than epsilon. So now I can take the maximum over j and the supremum over t to say that the maximum over j, the supremum over t less than t of this expression, it's bounded by the first one. Since x is bounded by epsilon, I would simply estimate x by epsilon. Forget about this expression. Since mu and g, it's a probability measure, this is bounded by c0 t times epsilon, and this bound does not depend on j and does not depend on small t. While for the second one, I have plus 2 times the maximum in j from 1 up to kn of the probability that x and j, it's larger than epsilon. Now, by assumption, if I send n to plus infinity, the second piece converges to 0, and that tells me that this limit, which is here, it's bounded by constant 0 t epsilon. So what we proved is that this limit here, it's bounded by constant 0 t epsilon. And since epsilon can be made arbitrarily small, we have that this limit is indeed equal to 0, and that proves the first part of the lemma, which shows that this condition implies the second condition. To prove the reverse statement, I have to remind you of a result which was telling us that if I take a probability measure mu and I compute the measure of the complement of an interval, say, minus epsilon, epsilon, this is bounded by a constant times epsilon times 0, 1 over epsilon, 1 minus the real part of the characteristic function associated to this measure, t dt. So I stated this theorem in a different way, taking epsilon equal to 1 over a. But if you replace 1 over a by epsilon, what you get, it's exactly this statement here. So I will use this inequality for by using the random variable x and j, and therefore the characteristic function here of f and j. So if I apply this, so if x it's a random variable whose distribution measure it's mu, this is exactly the probability that x it's larger than epsilon. And therefore, we have a bound of the probability that x is larger than epsilon in terms of the characteristic function, which I will use. So let me apply this inequality to the random variable x and j. So I have that probability of x and j larger than epsilon. It's bounded by c0 times epsilon times the integral from 0 to 1 over epsilon, 1 minus the real part of f and j of t dt. Now, I leave it to you to check, but it's clear that 1 minus the real part of phi of t, that this is less or equal than the absolute value of 1 minus phi of t. Right? If you separate the real part and the imaginary part of phi of t, you take the square, you will see that this bounds holds, and therefore I can bound this integral by c0 epsilon, the integral from 0 to 1 minus epsilon of 1 minus phi nj of t dt. Now, if I take the maximum over j on the left-hand side, I get that the maximum is bounded by the maximum, and the maximum of this integral is less or equal than the integral of the maximums. So this expression, well, if I take the maximum over j here, it's bounded by c0 epsilon, the integral from 0 to 1 over epsilon, the maximum for j between 1 and kn of 1 minus phi nj t dt. Now, this quantity here, remember the absolute value of a characteristic function is bounded by 1. So this expression here, it's bounded by 2 uniformly in n. And if I take what I know is that this maximum, the supremum for all t, it's converging to 0, so that if I take t in this expression to be equal to 1 over epsilon, I know that uniformly this expression it's converging to 0, it's bounded by 2, so I can apply the bounded convergence theorem to say that this integral it's converging to 0 as n goes to infinity, because, well, this expression, this function of t, it's converging uniformly to 0. We see you don't need the uniform, pointwise convergence will be enough, but we have still a stronger result of uniformity convergence. So as n goes to infinity, this expression converges to 0, and that proves that for any epsilon, the limit of this maximum converges to 0 as we claimed. So, and this completes the proof of this lemma. Now I will erase the lemma, I will recall the theorem, I will prove the theorem. So this is the theorem, again, we want to prove. So x and j, it's a sequence of independent random variables. So each row, it's formed by independent random variables. The row n has kn random variables. These two conditions are, you can always modify the row in such a way that they are satisfied. You can subtract, if these expectations are not equal to 0, you just subtract a constant. If these second moments are not equal to 1, you can just divide it by a constant to make it equal to 1. So these two conditions are not strong. We are just requiring the second moment to exist. And now here is the assumption we are introducing. We are asking the random variable x and j to be uniformly negligible in this sense, and we claim that under this condition, the Lindbergh condition holds if and only if the sequence converge to a Gaussian random variable. We already proved that if Lindbergh condition holds, then this sequence converge to a Gaussian random variable. Now, what we are going to prove is the converse. And if you wish, in the previous lecture, let me repeat that, we showed that Lindbergh condition implies this convergence and also implies this condition. So what we are now proving is converse of Lindbergh theorem, saying that if these two conditions hold, then Lindbergh is satisfied. But as I said, I want to understand these theorems in a broader context. So I'm assuming that we have negligibility. I want to investigate the convergence of these sums. And what this theorem is saying is that this sum will converge to a Gaussian if and only if Lindbergh conditions hold. So what I want to prove now, it's the converse, saying that, well, if this expression converges in distribution, if this sum converges in distribution, then Lindbergh condition holds. And in order to do that, well, so let's assume that we have this convergence. If we have this convergence, and if I represent by phi n the characteristic function of this sum, I know that phi n converge to the characteristic function of a Gaussian random variable of mean 0 and variance equal to 1, and which is exponential minus t2 over 2, and that this convergence holds uniformly in intervals, uniformly for t less or equal than t. So this is what we know from this condition. Now I want to use the lemma to say that the characteristic functions of f and j are very close to 1. So remember, it follows from the previous lemma that the supremum for t less or equal than t of the maximum of phi n j t minus 1. So phi n j, it's the characteristic function of the random variable x and j, that this converge to 0 as n goes to infinity. This means that if I fix a positive delta, I can find some integer n, which depends on delta and on t, such that this expression is bounded by delta for all n larger than n0. So I will consider only the n's which are larger than n0, so I will assume that this condition holds, and this means that phi nj of t is very close to 1, and therefore that the logarithm of phi nj is well defined, and I will also use this bound in order to do expansions of the log of 1 plus this quantity, of log of phi nj. Right? So let's start our proof. We know that this condition holds, and we wish to prove that this condition holds. So if I remember that these random variables are independent, phi n is the characteristic function of the sum, and we have seen that since they are independent, the characteristic function is given by the product of the characteristic functions. And now what this is telling me, let me take the logarithm on both sides. As I said, the logarithm is well defined because phi nj is very close to 1, so I can take here the logarithm of these quantities to say that we have a sum from 1 to kn of the logarithm of phi nj of t, which is converging to minus t2 divided by 2, and this uniformly for t less or equal than t. So we have this convergence, and what I claim is that the sum of phi n j t minus 1, it's converging to minus t over 2. So that this plus t2 divided by 2, that this quantity is converging to 0. So I will first prove that this is the case, so that my claim holds, and then I will come back and complete the proof of that this condition holds. So the proof is divided in 2 steps. I deduced from this condition that this sum converges to minus t squared divided by 2 uniformly in bounded intervals of t. Now I will deduce this condition from this limit, and then once I prove that, I will then prove Lindbergh's condition. So I wrote here what we want to prove, and here what we know. And here again, I'm sorry, but the proof will be very similar to part of the argument presented in the last lecture. So let me rewrite that sum, that expression, as a sum from 1 to kn. And here I use the fact that phi n jt, it's very close to 1, and therefore I want to do an expansion around 1 of phi n j t minus 1. So I'm just rewriting this as phi n j t minus 1 plus t squared over 2. And now I wish to perform a Taylor expansion of this expression. And remember, I know that the absolute value of this expression, it's bounded by delta for all j. So we proved that the maximum of the absolute value of this expression, it's bounded by delta, provided n is sufficiently large. So this is bounded by delta, and so I have the following expansion. This is equal to z plus a constant z over square, which means that the difference between log 1 plus z and z, it's bounded by a constant times z squared. And this because I know that this is bounded by delta. So I will use this expansion for this expression. So this is equal to the sum of 1 to kn. So this is our term z. So this is equal to phi n j t minus 1 plus t squared divided by 2. And then I have plus a remainder. And this remainder R and t, by that bound, it's bounded by the sum of phi n j t minus 1 squared times a constant. So by performing this expansion using this inequality, we can write this term as this one plus a remainder, and the remainder it's bounded by the square of the absolute value of this expression, and we still have a sum. So this is what I wrote. So if I can prove that the remainder converges to 0 uniformly for t less or equal than t, I can conclude from the fact that this expression is converging to 0, that this one is converging to 0. You see that what we have here, it's exactly what we have here. with this extra term. So if you can prove that this remainder Rn converge to 0 uniformly, it follows from this fact that indeed this supremum converge to 0. So we only have to show that the remainder converge to 0, and the proof of this claim, it's very close to the proof of a bound we proved in the last lecture. So let me show it again. We have to estimate this sum, and I will estimate this sum by, let's forget about the constant. So this sum, I will estimate it by a maximum times a sum. So it's bounded by the maximum for j between 1 and kn of phi n j t minus 1 times the sum. So if I can show that this term here converges to 0, and that this term here, it's bounded by a constant which depends only on capital T, and this is uniformly for all t less than t, then I'm in good shape, because this expression will be bounded by a constant times something which is vanishing also uniformly in t. Well, the fact that this expression here, it's converging uniformly to 0 has already been proved, because we have seen that it's equivalent to this condition. So the first term, it's indeed converging to 0. What we need really to do is to show that this sum, it's bounded. So let's prove that here. So let me write it. Phi and j, by definition, is the expectation of I, tx, and minus 1. Let me insert the minus 1 inside the mu and j. Now I can, since the expectation of x and j is 0, I can insert here a minus tx. So this is equal to the sum minus itx Now I can bound this expression by the same one with the absolute value inside the integral, and once I place the absolute value inside the integral, let me use the inequality that exponential iz minus 1 minus iz, it's bounded by a constant times z squared. So by using this inequality for z equal to tx, what we get is that this is bounded by a constant Now, t, it's bounded by capital T. So this is bounded by constant 0 capital T square. And what remains, it's the sum from 1 to kn of x squared d mu and j. But x squared d mu and j, it's here, it's equal to 1. The sum, it's equal to 1. So this is indeed bounded by constant times t squared. So that we have that this sum, it's bounded by a constant which depends on t. This maximum is converging to 0, and therefore we prove to claim that this expression is indeed converging to 0. Now I will erase everything. I will just keep that this expression is converging to 0, and from that I will deduce Lindbergh's condition. So in the first part of the proof, step 1, we concluded that this expression is converging to 0, and now let's complete the proof by showing that Lindbergh's condition holds. Now this is a complex number. We are saying that the absolute value of this complex number is converging to 0. That implies that the real part of this expression converges to 0. So this tells me that if I take the real part, what I get is here the real part of the characteristic function at time t minus 1, that this is converging to minus t squared divided by 2. And well, since I prefer positive expressions than negative expressions, let me rewrite, multiply by minus 1 this sum, and get that 1 minus the real part of phi and j of t, that this is converging to t squared. And well, if you remember the definition of the characteristic function, this is 1 minus the cosinus of tx d mu n jx. And this is converging to t divided by 2. Now I'll fix an epsilon, and I will consider this integral with x smaller than epsilon and x larger than epsilon. For x larger than epsilon, what we will do is that we'll estimate 1 minus cosinus tx by 2, and then since x is larger than epsilon, we'll estimate that by x squared divided by epsilon squared. So 1 minus cosinus theta x, it's bounded by 2. X larger than epsilon means that 1, it's smaller than x divided by epsilon, so I can introduce x squared divided by epsilon squared here to say that this expression here, it's bounded by 2 divided by epsilon squared divided by multiplying by x squared, and at this point I forgot about this set, d mu n j, which means that this sum in the pieces in which x is larger than epsilon, it's bounded by this sum and this sum by the conditions on the second moments, it's equal to 2 divided by epsilon squared. So we proved the following bound. We proved that the sum for j equal to 1 up to kn, so that the limit sup of this quantity, you see that this is positive, so these are positive real numbers, the sum is positive, and this limit sup, it's bounded by 2 divided by epsilon squared. Since this quantity here, it's converging to 0, what we can deduce from that is that this difference here, it's converging to 0. Now this sequence, it's converging to 0. Let me write this integral as x larger than epsilon, x bounded by epsilon, and what you get is that the limit sup of one minus cosine tx mu n j dx, minus t divided by 2. So if I rewrite this integral as two pieces, the first piece it's bounded by 2 epsilon. So this tells me that this limit it's bounded by 2 divided by epsilon square. Right? Because, well, just decompose this integral in two terms. First one, it's bounded by 2 epsilon. Since the limit is equal to 0, this means that the other piece, the limit sup of the other piece, it's bounded by 2 epsilon square. So it follows from the fact that this sequence is converging to 0 and that one is bounded by 2 epsilon, that what remains has to be bounded by 2 divided by epsilon. So let me continue from this fact that this limit sup is bounded by epsilon. And now let's observe the following. So let me use the fact the minus cosinus theta, it's bounded by theta squared divided by 2, and this is for all theta in R. So let me use this inequality. I leave it to you to check that this inequality is true, to say, well, that this expression here, 1 minus cosinus tx, it's bounded by tx squared divided by 2. Now, the integral of x squared with respect to mu and j and the sum, it's equal to 1. So this means that this expression here, if I take the sum, it's bounded by t squared divided by 2. This means that this real number here, it's bounded by t squared divided by 2. And this tells me that, well, so t squared divided by 2 minus, which is the sum from 1 up to kn, integral from x smaller than epsilon of 1 minus the cosinus tx mu n j dx, that this is positive, right? 1 minus cosinus tx, so let me repeat the argument. Let me use this bound. These bounds tell me that this expression is bounded by t squared x squared divided by 2. Let's forget about this restriction. The integral of x squared, when I sum over all j, gives me 1. So this sum, it's bounded by t squared divided by 2, which means that indeed t squared divided by 2, it's larger than this expression, therefore it's positive. And on the other hand, it's positive, but its limit sup is bounded by 2 epsilon. So 0, it's larger than this limit sup. And this limit sup, it's bounded by 2 divided by epsilon. Now, if I now divided everything by t squared, what I get is that, and let's say 2, it's t squared divided by 2. So I get here 1, I get here 2 divided by t squared, and here I get a 4 divided by t squared. And my claim is that this expression now what we know up to now is that this expression, which is positive, its limit sup, it's bounded by 4 divided by epsilon squared t squared. Now let's use this inequality again to show that, well, 1 minus cosinus, it's bounded. So this expression, it's less or equal than tx squared divided by 2. But with the minus sign, this means that this is larger or equal than minus t squared over square. And therefore, what we have, it's still that 0, it's larger or equal than the limit sup of 1 minus So I have here t square, which will cancel with t square, 1/2 which cancel with 1/2. I just have x for x smaller than epsilon of x square d mu n j and this is less or equal than 4 divided by epsilon square t square. So let me repeat again what we did. I used now this bound to have an upper bound for this expression, but since I have here minus sign, what I get is a lower bound for this expression. So this is bounded above by this expression, and the limit sup of this expression is bounded by that. So that tells me that indeed the limit sup of this expression is bounded by that, because this expression here it's less or equal than this one. It's still positive because if I forget about this restriction, here this is 1, and therefore this is positive. But now I'm in a good shape because what I'm saying is that, well, on the one hand this is positive, on the other hand this limit it's bounded by 4 divided by epsilon square t square. And here this term does not depend on t, so at this point for fixed epsilon I can send t to infinity so that I get that this converges to 0. That means that this expression here is converging to 1 as n goes to infinity. But 1 it's equal to this expression, this sum, so 1 minus this expression is actually equal to the sum from 1 up to kn that x larger than epsilon of x squared d mu n j. Right? We proved that, well, it's positive, this expression is positive, and its limit sup it's bounded by that. This expression does not depend on t, it's bounded by 1 over t squared, or 4 epsilon squared t squared. Send t to infinity to get that this limit it's actually equal to 0. If this limit is equal to 0, since 1 it's equal to the sum, what I get subtracting this expression to that one, it's exactly this one, and therefore this argument tells us that this term converges to 0, but this is exactly Lindbergh's condition. So we proved, indeed, that if this sum is converging to a Gaussian, then Lindbergh condition must hold. So that proves the point of this lecture is that Lindbergh's condition is a necessary and sufficient condition for the convergence of this sum to a Gaussian under this condition. So in the next lectures, I will keep this condition and I will look for other possible types of limit. I will say that, well, my first question will be assume that such a sequence converge. What can be the limit? Can be an exponential can be the limit. A Poisson distribution, a geometric distribution can be the limit of such a sum? First question. And then, well, for this class of distributions which can be the limit of such sum, what are conditions which guarantee that this sum indeed converges to that distribution?